So this video is sparked by a post where someone has problems with plotting some equation curves. This, like plotting equation curves in Inventor, is a problem on its own, but this one concerns let's say, a blower, rotor for the blower of this particular geometry. And firstly, this video should explain the geometry and how this works, and secondly, how to deal with it in Inventor so to get the useful effect. So firstly, let's see what we are dealing with here. So let's open the PDF. This is a roots blower, and it consists of two let's say gears or rotors, whatever you call it. English is not my first language, so I may, let's say, use wrong terms here, so please excuse me. So now we have two, let's say, gears that can either have 2 or 3 or potentially more, but I would not expect more than 3, let's say, lobes. And now there are a bunch of equations that are given here without any explanation, so I will not put too much effort in that because I will just explain it later. But now let's scroll down to here, where we have the geometry of this, let's call it a rotor for now. I don't know what's name. So this particular shape here given is the rotor with circular lobe. So this curve from here to here is a circular arc, and this curve here is not a circular arc. We know that this is a cycloidal gearing, so this curve will be a something related to cycloid. Now, once this set of gears rotate, obviously they are always in contact, and now we have a task of working out the exact geometry, let's say, of the gear. And part we know already, so we know from the definition of the task that this is a circular arc. We have few parameters here. So firstly, we have a center distance between these two wheels, which is given here as 2r, and r is the radius of the pitch circle, and as this is basically 1-to-1 ratio of this gearing system, so obviously both pitch diameters for both gears are identical because the two gears are identical. So now we know also that because the wheels are identical, one turn of each gear will result in full one turn of the other one. Therefore, we know that rotation from this point to this point needs to take 1/4 of the wheel, because this 1/4 of the turn. So this part takes 1/4 of the circumference of this let's say of the turn of the so 1/4 of the turn. So as it rotates about this point, so obviously the angle from here to here will be 1/4 of the full turn, or in more general, 1 over 2n when n is the number of lobes. So if there are 2 lobes, obviously it is 1/4. If there are 3, then it is 1/6. So we know instinctively that either it will be 45 or 30 degrees, depending on how many let's say, teeth or lobes we have. So let's start working this out in Inventor. We will need a part that for convenience we will use some parameters. So firstly, center distance. This is, let's say, we will change it later, but for now assumption is 80 millimeters. Then n, this is number of lobes, which is 2. Then r obviously is as defined, center distance divided by 2, and a is a parameter. It's the distance between the center. What is this distance? It is a distance from center of the gear to the center of the arc or circle arc that it forms the lobe. So in our case, for convenience, we define it as r minus a value. So these values are constant as for the geometry, although they are parameters. So now let's work out a few things in a sketch. So let's do firstly n circle, and now radius. This will be r. So now this is our let's say pitch circle or pitch diameter of one gear. Now let's get a line which will define one of our axes, which will be vertical. And now let's make another one from here. Let's say to whatever, to here. And now define this angle as 360 by n by 2 and then by 2. degrees. Okay, so now this being on the other side, obviously will form a one quarter of a circle. So obviously we have this, and now if we change n to 3, let's make it smaller. This is not really working. So let's change it to 3, and we can see that this follows. So let's stay with 2. Now we know that the lobe will be from here to here, and the other one will be from the other side. So let's make a lobe from here. Oh, come on. The screencast is actually making it so slow. And now what we know about this part is that it actually is in a distance from here to here that is equal a. So now, depending on a, this will also change. So r minus 5. So as we change it, this changes. So let's say change it a bit more, r minus 20. So you see, this follows. But let's leave it like minus 5. Okay. So now if we change again n to 3, where is 3? This also changes, as you can see. So now this is our, let's say, one lobe of one of our wheels. Now there will be a second gear with the same diameter as the first one, and obviously it will be in constant distance of 2 times L, or center distance actually. This will make it, let's say, rotating around. And now we can see this set of wheels as either rotating together about some point in the middle, or we can also see it as one wheel rotating around the other one that is stationary. So like this. And this we will use to solve this geometry. Now, obviously, we will need an input angle, which will be the angle that this wheel rotates around. So we have some reference. Let's get it here. And now this will be our input angle. So what's the name? D5. So now what happens? So let's position this right here for now. So no, I don't want to constrain it. Okay, so let's say this is a starting position, and now as this wheel is exactly the same as this one, so let's assume that it will be positioned so the lobe is here, and then we will try to find this convex curve that fits on the bottom wheel. So let's get this out for now. Let's define a fixed geometry. So let's define a two lines in here. Obviously these wheels are the same, so this is equals, and the other one equals, and obviously I don't want that. Why this is here? Oh, please. And now we want the lobe, which will be from here to here, with obviously center point located on this line and in the distance A. Okay, so we have this wheel, and now if we drag it, let's say, we see that basically it travels like this, which is not actually how it exactly works, because while this rotates around this point, also this wheel will rotate around its center. So let's fix it for a moment. And now we need to establish how this rotates. So we know this is twice this angle for simplicity, and now the line here, which will be in the middle. Okay, so let's this is our axis. So let's make it like this, and then this is constant. Come on. We're over constrain the sketch, very interesting. Okay, because this landed in the middle. So we now have this thing. Now, how much does it rotate? So we know that for the full term of the system, so as long as it takes this wheel to rotate around, this wheel will rotate once around its axis. So this is actually equals this one. And now if we see, when I rotate it, you see this will be the action that it takes. So it takes one full turn. Inventor is getting slower and slower, so I need to go back. So now what we need to establish is the geometry of this rotation from 0 to 45 degrees, because rest will be either symmetric or mirror. So what we are now looking for is curve that is basically produced by the tangent of the tangent to this lobe going through a contact point. So where will be the contact point? Well, the contact point is kind of tricky because where will it be? So we have to use few basic principles. So this is rolling. This is rolling on some surface. If it is rolling, then obviously the contact point will be where the radius of this circle meets the circumference. So we will make radius. Radius always goes from the center to here. But now, where exactly? Because we can choose, like, let's say, let's fix it. And now we can choose any point here. So we also know that because these are two wheels that altogether form a, let's say, rolling mechanism, this line needs also to go through a point where the center, the line that connects the centers of these wheels crosses with the pitch circles. So I will make a point and I will force this point to be on this line that connects those, and also here, and it will automatically be also there. And now, so Inventor doesn't actually lose it, I will use a line that goes from here to here, and also from here to here. And now I know these lines are collinear. And now I have a line, come on, and now I have a line that actually produces the contact point. You see, when I roll it to 45 degrees, this line actually is exactly where I need it to be. So now the task in hand is to define the curve that this point travels from here to here, because rest we know that the rest is like this. So then there is another one. So let's say because the rest is exactly the same. So we know it from here to here, and this is the slope, and now this is A. So here we know we need it from here to here, and we know that from here to there it will be symmetric. So now, how do we go about finding this equation for this curve? Well, we can go, let's say, two ways here. One is to just use basic maths and trigonometry to get analytical equation for the curve that basically this point travels on. And second approach is to use the similar approach as it is used to plot the gearing curve for a cycloidal disk in a cycloidal drive that uses a set of round pins as a outer wheel gears. This is used in a cycloidal gears or let's say transmissions that have very big gear ratio, and they are used in, let's say, power transmission for heavy applications, or not heavy, but with. I'm not an expert. I use it for some other project, but so basically, these two methods. There is also a third one, but let's say these two methods will give us this exactly the same result. So one is the first one is we make a curve that is basically cycloid of this point when this wheel rolls around this one, which is very easy, and then we offset it by the radius of this arc. And it's not complicated to do, because to get this equation for this cycloid is quite easy. But it does require to do an offset, which is easy in Inventor because this is quite easy to do, but not so easy if you want to analytically do it. And the other one will be just similar, only we will get equations straight for this point. So now I will pause for a moment and I will record the next part of this video next day.